This video will demonstrate provably correct high-level control of real and simulated robots with the LTLMoP toolkit, the OMPL motion planning library, and ROS. In this example, we'll have the robot act as a waiter in a small restaurant, taking orders from 2 customers and bringing them food from the kitchen when it's ready. The task specification can be written in LTLMoP in structured English, as seen here, and compiled into a controller. In this case, however, we see that a controller could not be generated because no controller exists that is guaranteed to succeed in all scenarios. To determine the problem, we use an interactive game. The user plays as the robot, trying to follow the specification despite an adversarial environment. By playing the game, we realize that we need to add an assumption to our specification, that food will always eventually be ready. A controller can now be generated from the specification. Now let's take a look at this controller in action. First, we have a PR2 simulated in Gazebo. It receives an order from Spiros, and, having also received the food ready signal, goes to the kitchen to retrieve food for him. In this case, the order and food ready sensors are simulated with on-screen buttons. The perception and grasping is handled by the ROS PR2 libraries. Now, food in hand, the PR2 heads back to Spiros to complete delivery. The robot will continue to follow its specification indefinitely, continuously servicing orders as they come in. Now, the same controller will be used to control a real Aldebaran Now in our lab. Spiros orders for both himself and Cameron, and once the food is ready, the Now goes to the kitchen to retrieve and deliver the dish. Orders are given using printed 2D barcodes on the menu, and the food ready signal is detected with a simple electrical contact switch in the kitchen. Localization is provided by an overhead Vicon system, and motion planning is done using OMPL's RRT-Connect implementation. Thanks for watching. For more information, please visit our website.